So for question 4, you really had to set up and figure out the rate law for this whole reaction. And yeah, my son was using my iPad to color earlier today, so all the colors are going to be giant. So we hopefully came together, figured out the rate law for this reaction, and you figured out something like rate equals the rate constant times the concentration. I think it's iodide to the first, and then the SO8, yeah, 2 minus. I think that's a second order relationship. So basically, right, we found this relationship answering the previous questions. Now that we found the rate law for this reaction, all you want to do is just go to one experiment and pick the concentrations from that experiment, the rate from that experiment, and just plug it all in. So we'll go back, we'll grab experiment 1. All right, there's my concentration, 0.075, 0.9, and 516 times 10 to the minus 4. Plug all of that into the rate law that you came up with. So 5.16 times 10 to the minus 4 equals the rate constant, 0.075 to the first. And I think this was like a 0.9. Right, so from there, I forgot to get my calculator out. Or I did, and I just misplaced it. I'm just going to mute the video for tonight because it's just going to be all over the place because I'm on my iPad. So we just multiply those together, right? We square the 0.9. So 0.9 squared times 0.075. So we get 5.16 times 10 to the minus 4 equals my rate constant times 6.075 times 10 to the minus 2. Right, we're going to just divide across to solve for K, our rate constant. So 10 to the minus 2 times 10 to the minus 2. And we get the rate constant for this reaction. Let's see, 5.16 times 10 to the minus 4. Divide that by my answer. And I get something like 8.49 times 10 to the minus 3 for my rate constant. So that's all that was asking. We came up with the rate law in question 1 and question 2, and then in question 3, it asked for the overall order. But question 4, we're going to use that rate law now to find the rate constant. And we're going to do that by basically just going to that experiment, going to that data table, and plugging in concentrations and rate data from that first experiment. Yeah, there was a lot of questions on question 9 as well. I think that came up in office hours. That also came up in class, I think, one day as well. So, right, I can't stress this enough. Read the question, right? Read all the information they give to you. So the data below was collected for a first order reaction, and that's key to solving question 9, is that this data came from a first order reaction. Because this data came for a first order reaction, we know natural log of concentration time t equals negative kT plus the natural log of our initial concentration. We know we can use the integrated rate law for a first order reaction. So from there, we're just going to plug in the concentrations. So, right, natural log of some point in the future, my concentration is 0.05. I'm looking for the rate constant, so that's K. And what point in the future is this, right? This is 8 seconds in the future plus natural log of my initial concentration, which is 0.1. So natural log of 0.1, we get minus 2.30 natural log of 0.045, and I get minus 3.10, right, equals a negative k times 8 seconds. So we're going to add this across. We're going to add the 2.3 across. All right, we add the 2.3 across. And I get negative 0.801 equals a negative k times 8 seconds. So we're going to divide by that negative 8 seconds, right? We want to get rid of that negative sign as well. So we divide by the negative 8. And we get a rate constant of, 0.100 inverse seconds. So that should be choice A for question 9. Some people wanted to do, change in concentration over change in time. That would be our rate. It's not asking for the rate. It's asking for the rate constant for the reaction. So the fact that it's asking for the rate constant and the fact that it tells us it's a first order reaction lets us know we want to use the integrated rate law for a first order reaction to solve for K, our rate constant in that reaction. All right, any questions on 9 before we move on to 10? Is the audio okay? All right, thank you. So yeah, in question 9, right, we found the rate constant is 0.1. And so now that we found the rate constant, right, we can find the concentration after 20 seconds. Because again, this is still a first order reaction, right? So natural log of concentration time t, negative kt, plus the natural log of our initial concentration. So from there, all we want to do is plug in what we know, right? So we're looking for our concentration. At 20 seconds in the reaction, we know our rate constant is 0.1, right? And that is inverse seconds, 20 seconds into the reaction, plus the natural log of our initial concentration. Our initial concentration was 0.1. So do a little bit of math here. All right, we already did the natural log of 0.1. And then we're going to add that to a negative 0.1 times 20. And so I get natural log of concentration at time t equals negative 4.30. And here was the trick that we talked about in class, right? It's, it's less chemistry, it's more math, but the opposite function of natural log is e, and we need to get rid of the natural log. So if I, right, e raised to the natural log of concentration equals that concentration. So we need to get rid of the natural log. So if I e to the natural log of concentration, because I do that to the left side of the equation, I'm going to take e and raise that to the negative 4.3 on the right side of the equation to get my concentration, right? So second e to negative 4.3, and I get a concentration of like 1.35 times 10 to the minus 2, which is hopefully Yeah, I would go with choice 2 there, right? We would round that up to 1.4 to would be our closest answer there for question 10. So really we needed the rate constant from the previous one, and we needed to know that it was still a first order reaction. So we could still use the integrated rate law for a first order reaction to solve this problem. All right, let's see, question 12, 13, and then 15, and we'll call that our first part of the video. Yeah, question 12, I worked through this, I think, probably 2 or 3 times just today in office hours. Once you start it, it's kind of straightforward, right? They give us the rate law. The rate law is rate equals the rate constant times the concentration of A squared, B to the first, C cubed. And they tell us that when all the concentrations are 1 molar, that our rate is 3 molar per second. So we have to do the same calculation twice. We're basically just going to plug in and say, okay, the rate is 3 molar per second. I don't know the rate constant, but I have that rate when I've got 1 molar A squared times 1 molar B to the first times 1 molar C cubed. Multiply those all together, I get 3 molar per second equals K times, that's third, so that would be 1 molar to the sixth. Divide by 1 molar to the sixth, right? And we get a rate constant. My rate constant for this reaction is 3. You know, the units aren't really important, but those are the units. Now that I know the rate constant for this reaction, now we can figure out the rate at any other concentration that we have, and we happen to have 2 molar concentration. So now I'm solving for rate, right? Rate equals, well, my rate constant is 3 molar to the negative fifth inverse seconds times 2 molar squared, 2 molar to the first, and 2 molar cubed. Multiply those all together, and we get a rate of approximately 192 molar per second. They're looking for the answer in terms of 2 significant figures, so 2 sig figs, right? We would just say rate is 1.9 e to the 2 molar per second for question 12. All right, for question 13, I guess maybe it's just the way it's worded is making it kind of a tricky question, right? Question 13, the equilibrium constant, right? Expression depends on what? So the equilibrium constant, right, is just K, and that is the concentration of products times the concentration of reactants. And if we had a reaction, right, nitrogen plus hydrogen going to ammonia, and that's a gas, and that's a gas, and that's a gas, right? Our equilibrium constant expression would be the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. So where did we get that expression from, right? What did this expression depend on? This expression just depended on the reaction, right? And the coefficients of that reaction, or the stoichiometry of that reaction. That's all that this depended on. So if we take a look at the choices here for question 13, right? Doesn't matter the mechanism. We didn't really get into that, right? Again, we don't know the mechanism for this reaction. nothing to do with temperature. I mean, certainly the position is influenced by temperature, but in the expression, right, we don't need temperature to set that up. Quantities of reactants and products that are initially present, no, we didn't need that, right? It just depends on the stoichiometry of that reaction. All right, question 15, and then we'll take a break there. Oh, yeah. Okay. Question 15, we don't have to do a calculation, but we could do a calculation if you wanted to for question 15. Right, a compound decomposes by a first order process if 12.5, and this is important, if 12.5% of the compound remains after 60 minutes, what is the half-life of the compound? So I'll show you the easy way, and then I'll show you the other way in case the easy way is not an option. We can only do the easy way in this case because if you start with 100% of the material after one half-life, you'd have 50%. So there's my first half-life. My second half-life would leave us with 25%, and my third half-life would leave us with 12.5%. So essentially, I've got 3 half-lives to get to 12.5%, and that took 60 minutes, right? So 60 minutes divided by 3, right? Each half-life was 20 minutes. We can only do that because 12.5 is a nice round half-life. If they told us 17%, right, or 37%, or 42%, right, if they told us some weird percentage that did not fall in a nice clean half-life, then we would have to do a calculation. And that calculation would look like, we know this is a first order process, so natural log of concentration at time t, negative k t plus the natural log of concentration at time 0. So what we would have to do is say, okay, at time 0, I had 100% of the material, and I'm looking for at what point, right, did I have 12.5% of the material? I know that took 60 minutes. But to use these percentages in our calculation, we need to use them as a decimal. So we would say 0.125 would be that, and 1 would be that. So we plug everything in, right? Natural log of 0.125 equals negative k. We would have to find our rate constants, right? 60 minutes plus the natural log of 1. What's nice about this is the natural log of 1 is 0, so that goes away. So the natural log of 0.125, I get a negative 2.079 equals negative k 60 minutes. Divide by a negative 60 minutes. And we get a rate constant for the reaction, right? Divide by negative 60. I get a rate constant of like 3.466 times 10 to the minus 2. Not done there, right? We still haven't found the half-life, right? T1 half equals 0.693 over K. So T1 half equals 0.693 over 3.46 times 10 to the minus 2. All right, what does my half-life equal? 0.693 divided by, all right, lucky. We got 19.995 minutes, right? Pretty close to the same thing we got up here, 20 minutes. So if it's a nice clean half-life, we can do this simple trick of just divide by 2, divide by 2, divide by 2 each time, adding the time required for a half-life. If it is not a nice clean half-life, then we would have to go this route. We'd have to use integrated rate law for a first order reaction, use our initial, even if we don't know, we could just say 100% because that's what you'd have at the start. We would need to be told what percentage we're looking for, but we want to use this as a decimal and not as a percentage. We would be told the time between those two, right? And from there, we could find the rate constant. Once we find the rate constant, then we can use our half-life equation to find the half-life for that reaction. So a little bit more involved if you don't know if it's a nice clean half-life or not.